Thanks the organizers for giving me this opportunity. So this is my pleasant duty to end up today's talk. And after a heavy meal, a light dessert may be good. So my talk doesn't contain much mathematics, almost like Ranjini's talk in the morning. It's rather data analysis. So it is done in collaboration with Shitabhra Sinha of IMSC Chennai, and it is funded by ITRA Media Lab Asia. So let me first tell you what it is all about. So congestion in urban traffic flow is characterized by waiting time distribution. So waiting time distribution is the thing which will tell you whether traffic is congested or not. And by waiting time distribution, I mean the probability that a car is stuck up for a time tau. So the probability p tau is the probability that it is stuck up for a time tau. Now, if the p tau versus tau curve looks like this, then you can see all the cars are stuck up for only a small amount of time. So the probability that it will be stuck up for a very large time is almost nil. So this means smooth flow. And then if this curve looks like this, then the probability that the cars will be stuck up for a large time is high. So this means traffic jam. So just by looking at this p tau versus tau curve, the waiting time distribution probability, we can say whether there is traffic congestion or not. So the outline of my talk is like this. First, I shall present analysis of some real live data for traffic congestion. And then I shall present a model explaining the results. And this model is based on what we call aggressiveness, or it may be called priority of the drivers at the traffic signals. Okay, so available data. This is some serious issue. So we have got some non-trivial data, GPS data of about 1,000 taxis in Delhi, Bangalore, and Mumbai. Each, 1,000 taxis in Delhi, in Bangalore, Mumbai. 1,000 in Bangalore, 1,000 in Mumbai. For several months in 2013 and 14 is available. This data analysis was done in collaboration with Jagannathan of IIT Madras. For each vehicle, the data available is time, the coordinates of the vehicle, and the velocity. So at every time instant, I know where the car is and what is its velocity. Of course, for some cars, every car has an identification number. Now, it might happen that for one car, I'm finding that the velocity is small for a very long time, maybe 1 hour or 2 hours. Then that data is useless because then the car is probably in the garage. Okay, so the data available looks something like this when averaged over many days. So this is average number of taxis, averaged over many days, and this is time of the day. You see, the number of taxis is very low in the morning, although not very low, and then it rises around at this time, and then it is very low at midnight. And this is the average speed. So average speed, it is averaged over all the taxis. And this is very low during office hours, and then it rises at late hours. Okay, but this is not the data we had analyzed. Actually, we had looked at the data of every vehicle and tried to calculate the probability distribution function. So we have measured when a car has speed less than, say, 10 kilometers per hour, this is the threshold velocity, I'll come to this later, for tau seconds. So if I find that a car has speed less than 10 kilometers per hour for 10 seconds, and then the velocity rises, then I shall say that it was in a congestion for 10 seconds. So the thing is, before and after this interval of tau seconds, the speed was higher than this threshold. So we compute the statistics of this tau for all the cars on all the days to obtain the probability distribution function. So for every day, I looked at every car and see for how long together, for what length of time the velocity was less than the threshold. And of course, some data had to be rejected because, we had to reject the data for the cars which was in the garage, etc., etc. Okay, so what is the result? This is the result. April 2013, average only on weekdays and the threshold 10 kilometers per hour. Okay, this blue one is the data for Bengaluru, and it is almost algebraic. Note that this is a log-log scale. But one more thing, here the x coordinate is 10 to the power 4, and 10 to the power 4 is more than 1 hour. So one should not trust the data for large x values. But in any case, this looks like an algebraic decay. And this red one is for Delhi. This also looks like an algebraic decay. And the black one is for Mumbai. So these are the exponents. And so we conclude at least this figure seems to indicate that the probability decays algebraically and it is scale-free. So the questions come up: why it obeys a power law, and can any microscopic model explain it? Actually, this data analysis was presented by Majid, Rajakumar, and Sinha in 2016. Okay. Yes, please. This is difficult to say. Yeah. Yes? Okay, so next is the dependence on threshold velocity. You see, this one is the curve for Bangalore, and you might think at first sight that this is going very nicely like this, but it is not so nice. There are some points over there, and analysis of real life data is always like that. I mean, some points are complicated, difficult to explain. Rather, this blue line, which is for Bombay, they seem to converge to this point. And this one for Delhi, they also seem to converge. So we can say that the threshold is somewhere between 2 to 3, or rather 2 to 2.5 for all the 3 cities in India, according to the data available. So we don't know what will happen if we could collect the data of 2016 or 17 and repeat the analysis. Okay, so now some more data. For a motorway in Germany, these people, Schreckenberg's group, made the same analysis. And you can ignore these colors because these colors actually refer to different traffic intersections. And an average shows more or less an algebraic decay, but here the exponent is much less, it is 1.5. Okay. So now the model. Okay. So consider a traffic bottleneck where only one car can pass through. And let us say that the most aggressive driver will pass. If you do not accept the word aggressive, then you can say that, there is some priority list, and in some peculiar way, one car is getting higher priority. But there is nobody standing at every signal and assigning priority to the drivers. Anyway, so we make some hypotheses which might seem a little bit drastic. So aggressiveness, our hypothesis is aggressiveness can be quantified by an attribute A, some number A, and it depends on 2 factors. One is intrinsic nature. So, I mean, Shamriddhi may be a more aggressive driver than me, and Abhishek may be a less aggressive driver than me. Okay, so and okay, and also sorry, what happened? Yes, and also on the duration of waiting. So as I wait more and more, I become more and more impatient and my aggressiveness grows. So now some more, precise hypothesis. The aggressiveness, which I said that we can quantify by an attribute A, we write it as n times tau to the power sigma. It is an arithmetic product of a quantity n, which varies randomly from person to person and is uniformly distributed between 0 and 1. So it is randomly distributed among the drivers. But this sigma is the same for all persons. We shall mention later that we have tried some other forms also, but they did not reproduce the real data. So using this hypothesis, one can show that numerically and analytically one can derive the waiting time distribution, and that waiting time distribution gives an algebraic decay where this exponent is this exponent sigma plus 1. So this exponent actually describes how fastly I'm getting more and more impatient. So this index is actually this index plus 1. So it shows that sigma is 1 to 2 in India and 0.5 in Germany. So maybe Indians get more and more impatient very quickly, and Germans do not get impatient so quickly. Anyway, the crucial thing is this hypothesis reproduces this waiting time distribution, and the precise algorithm is we start at time t equal to 0 with a queue of L cars with these n values drawn from a uniform distribution, and then at each update the car with the highest A goes off and is replaced by another car, and for the removed car the waiting time is naturally t minus t0, where t0 is the time step at which it was introduced. The new car has an n value drawn from this random distribution. And okay, so the number of cars remain constant in this model. So a few observations: choice of the functional form, some functional forms other than this does not reproduce the observed trend, and similar result is obtained if the total number of cars vary randomly about a mean value, and if we consider several rows but follow the same principle that the car with the highest A value will pass, then also the same result is obtained. So this is the summary, that this hypothesis reproduces this sort of waiting time distribution, and so in India, this index, which describes how fastly one gets more and more aggressive with waiting time, that is higher in India, seems to be higher in India than in Germany. But the most crucial thing is this caution. Data for 3 cities in India in 2013 and 1 city in Germany in 2016 show that probability distribution of congestion time is this. So before we take any serious conclusion, similar analysis of data for many other places need to be considered. Okay, thank you. And sorry for the delay.
Questions related to that?
To understand one power law.
Sorry?
To understand one power law, we introduce another power law which you don't understand.
To understand one power law, I introduced another power law because of
the power law in, power law out. So, but it just
if I use some exponential law or some other rule,
you will not get.
I will not get it.
So basically, power law in, power law out. So we don't understand this power law, and to understand one power law, we introduce another power law. Or maybe this power law indicates that dependence of A on the waiting time is also a power law. Yes.
Yes. Is it? Excuse me. Yeah. It is known that you can get power law behavior by the sum of many weighted exponentials. So
Yes.
could that be an explanation?
Yes, but
Because the power law doesn't seem universal. Like it's not one power law for all three cities. So it's
it's power law
possible.
with different exponents. Different exponents. Yes. Um, well, I do not know. Actually, we tried to obtain this power law through from superposition of exponentials, but there were many troubles. I mean, he's saying superposition of power law, superposition of exponentials gives power law only with integer exponents. I do not know. I do not know. Yes. Any other question?
Yeah. So does the aggressiveness depend here this way?
Yes.
Does the aggressiveness depend on which car you are driving? Because if you drive an ambassador taxi and there is a Maruti car, I mean, no matter how aggressive I am, I will just go pass by the Maruti car.
Actually, there is a prefactor n which varies randomly from one vehicle to another.
Okay.
Is there any more questions? So let's thank the speaker once again, as well as